Hey guys, welcome back. This is Professor Roldan. This is College Algebra, Section 1.4, Complex Numbers. You do have to excuse me. I do have a sinus cold and congestion, so I do sound a little different today. Hopefully I can get better this week. So again, this is Professor Roldan, 1.4 Complex Numbers. So let's get started. The imaginary unit, I, is defined as, and we are going to be doing, you're going to be seeing some of these in solutions of quadratic functions and other functions. So it is important to kind of review some of these things and get through the basics. So first things first, I is the square root of -1, okay, which before this course you would get undefined or error as an answer or not a real number. Well, now it is even though that's true, it's not a real number. We need to use imaginary numbers now. Okay, so this is created to be able to deal with certain functions, which you'll see in a minute. So I squared is going to be -1. Okay, so for example, the concept of, let's see, the square root of -16, that's basically impossible. You put this in your calculator, you're going to get an error message. Now, most scientific calculators can do some extra things with this, but basically what we're going to be doing is taking out the square root of -1. Separating that out from the 16, the square root of 16, so that since we know the square root of -1 is I, this gets replaced, and the square root of 16 is 4, and we call this answer or solution 4I. Okay, well, again, complex numbers. Basically, complex numbers look like this. So A plus BI, where the real part is the regular looking number. There's no I next to it. And then the one with the I, that is the imaginary part. So, complex numbers, you can have the imaginary part there, or you can have it missing. So let's take a look at kind of, so real numbers is when your A plus BI has B equals to 0. So the reason why you don't see it in a regular number is because the I disappeared because it got multiplied by 0. Okay? And then imaginary numbers has A plus BI with some number for B. So it does not equal to 0. So it could be 5I or 4I or -10I or whatever. Okay, so we're gonna, and so what, the question is, why are we even looking at this? Why even bother with imaginary numbers? Let's take a look at these two examples here. I'm going to change this first equation to x squared minus 1. Okay, x squared minus 1. Okay, so looking at x squared minus 1 equals 0 versus x squared plus 1 equals 0. Well, if we add 1 to both sides, we're going to get x squared equals 1. So basically that's saying what times what equals 1. Okay, it has to be the same exact number. So we want to go ahead and take the square root, and that's going to give us plus or minus 1. Okay, so 1 times 1 is 1. Also negative 1 times negative 1 is 1. But when you get to this other scenario over here, if we subtract 1 from both sides, we're going to get x squared equals negative 1. So you can see that what the problem is going to be when we take the square root. That is an issue, okay? So we solve this issue by replacing this with an I, okay? Plus or minus I. And we'll get into this later down the line here, but visually speaking, I just want to show you that if you have a graph, these two, the plus or minus 1 is basically this quadratic here with negative 1 there and positive 1 or that's where these come from. Okay, but what if your parabola does not, or your quadratic function does not intersect the x-axis? Something like this. Okay, it doesn't cross the x-axis, so there is no solution. But we say that there's no real solution, but there's as you can see, two imaginary solutions, plus or minus I. Okay. All right, so that's kind of the visual and why do we need this type of setup here. So let's start digging into some questions here. So first of all, we're going to classify the parts. Okay. So the real part is right there. Imaginary is right there because it has an I. This one is only the I that you can see. That's the imaginary. So where's the real? Well, it must be 0 because it's not there. Okay. And this one only has the real part, but the imaginary is missing because, well, you guessed it, b is 0. Oops. Okay, so if b is 0, 0 times I is 0, so you don't really see it, but there it is. Okay. Okay, so let's take a look at operations with complex numbers. And so the strategy here, we have two complex numbers being added together, or number 5, we're subtracting them. So basically, you want to combine like terms. That's our strategy. Okay. They combine like terms where the I is basically behaves like a variable. Okay, so like an x, for example. So if they have i's, they're like terms. Okay. Okay. So the mental math that's happening here is basically the real parts we're going to add up. So that's the 5 and that's 7. And then the imaginary is the negative 11i plus 4i. So basically, we're just doing 12, and then negative 11 plus 4 is negative 7. We'll keep that I in there. Okay. So that's kind of what you want to do in your head. So we don't have to keep grouping them like we just did, but you can if you want. And I'm not going to keep doing that. So we can distribute the negative here. So we can rewrite this as a positive 11 and positive 6i. And then we have our real parts right there, which is 6. And our imaginary parts right here, which is 7. Okay? Okay. So now you try. Go ahead and try on your own 6 and 7. Pause the video, see how you do, and then unpause it, and you will see the solution. All right, see you in a few minutes. All right. So hopefully you got 11 minus I for number 6 and 3 minus 6i for number 7. Okay. Feel free to pause it and check that out. We're going to move on. So when we get to number 8 here, we are multiplying. Okay. So when we're multiplying, you just need to remember that I squared is negative 1. We said that at the beginning. I squared is equal to negative 1. Okay, so the mental math that we're going to do here, okay, is basically we're taking our two coefficients, 2 times negative 3, thinking those two are grouped together, and then basically I times I. That's kind of what's going on in our minds. So this is going to be negative 6 times I squared, and then I squared becomes negative 1. Okay. So negative 6 times negative 1 is positive 6. All right, let's go to the next page. So number 9 in your workbook, we have, in this case, we have a monomial term outside the parentheses. So the strategy here is to distribute. Okay, distribute the monomial. The monomial is sitting right there. It's one term, and we're going to multiply those two across. So 4i times 3 is 12i, and negative 24i squared. Okay. So the 12i, we're going to replace that I squared with a negative 1, and then negative times negative is positive. And you can leave it like this. You don't have to switch it up if you don't want to. Okay. Let's do another one. So this one, we want to distribute the binomial this time. Okay, which the binomial is going to create this FOIL strategy. Okay, first, outer, inner, last. And what I mean by that, we're going to distribute one piece at a time. Okay, so the 7, the first term, gets distributed So 7 times negative 2, that's the first terms. And then 7 times negative 3i, that's the outer terms. Okay, so basically we're doing, let's see here, f. So 7 times negative 2, that's the first terms, that's negative 14. The outer terms is going to be negative 21i. And then we're going to go to negative 2i and distribute this over. And basically, those two in the middle are called the inner terms. And then the last arrow, your fourth arrow, is the L, or the last terms. So the inner terms is going to be negative 4i, and the last terms are positive 6i squared. So that's what I mean by FOIL. You don't really have to use that. If you've never used it, it's fine. It's just a little cool word that helps remember the 4 arrows. Basically, you just need to remember the 4 arrows. Okay. So what happens now is that we have these like terms right there, and we also know that the I turns into a negative 1. So negative 21 minus 4, same sign at find the sum. Keep this sign, so it's 25i. I'm sorry, that's supposed to be a positive 4. Sorry about that. So we're subtracting different signs, find the difference. Keep the sign of the larger digits, so it's negative 17i. And then 6 times negative 1. And so now we know we're going to do 14 minus 6. Okay, so that is negative 21 minus 17i, and we are done. Okay, so why don't you try numbers 11 and 12. Okay, pause the video, see how you do, and then check your answer when you're done. Okay, so for number 11, should have gotten negative 10i plus 10, or 10 minus 10i. Doesn't matter which way you write it. Because of the associative property, lets us rearrange things. It's fine. Number 12 is 28 minus 44i. Okay. Okay, so number 13, we get to a weird looking binomial with a power of 2. And so we're going to use basically the definition of powers of 2. And that means to repeat whatever is in front of it twice. Okay? So basically this is 1 plus I and another 1 plus I multiplied together. So we're going to go ahead and do our distribution of our 4 terms there. So we get 1 plus I plus I plus I squared. And we know this becomes a negative 1. So basically we're going to do 1 minus 1 is 0. And these two become 2i. Okay, so let's go to the next page. Okay, so we have here same deal. So it's 9 plus 15i. I'm sorry. Let's do that again. So 9 minus 15i plus 15i minus 25i squared. And then we know this becomes a positive 25, negative times negative. So again, we're going to put our two real numbers together and combine our imaginary part. So it's 34 plus 0i, which is just 34. Now I want to point out some observations here. Okay, from this. So first of all, I don't know if you noticed these terms or these two binomials. They basically have the same, it's the same terms. Okay, 3 and 5i, but opposite middle signs. Opposite middle signs. And this relationship is called complex conjugates. This relationship is called complex conjugates. Okay. Now, what's so special about that? Why is there a fancy name? Well, let's take a look at what happened. And as you can see right here, our imaginary terms got canceled out there. And of course, the I squared turns into a negative 1. So all the imaginary terms disappear because we have this 0i. And so now this is what's called a real number. Okay, it doesn't have any imaginary parts, so that's very helpful in some cases. We'll see in a minute. So basically, another observation that we just seen is that the multiplication of complex conjugates, as you just saw, produces a real number. Okay? In other words, what I mean by real number is that the I term is eliminated. Okay? Now, we also have seen something like this in Algebra 1 when we're multiplying binomials. There's a shortcut here. So whenever you have A plus bi, and then the exact same terms, but opposite middle signs, that's always going to produce the two middle terms of FOIL, O and I, they cancel out, they disappear. So that basically leaves you with the front terms, which is in this case A times A is A squared, and the last terms, which is bi times bi, which is a negative bi within negative bi squared, and that turns into basically a positive b squared. Okay, it's a positive b squared. So we're gonna remember that shortcut. So let's go to number 15. And it's a little small, so I'm going to zoom in some. Still got to write some more. So if you look at 15, say, okay, 5 plus 4i divided by 4 minus 5 right now. What's what's wrong with this expression? I mean, it doesn't really, it's not really apparent. There's something that needs to be done to this. So what needs to be done to this expression? You may be asking, what's wrong with this? Why do we have to do anything to this? Well, there's a little rule that you have to follow, and that is just like you can have negative exponents in an answer, or unsimplified fractions in an answer, stuff like that. So this is another one, and it's no imaginary numbers in the denominator. Okay, if you remember, that's the bottom part. So that's our rule. Well, what's our strategy? Well, we just figured out something that makes imaginary numbers disappear. That's the complex conjugate concept, multiplying complex conjugates. So that's what we're going to do here. But we're not allowed to change the value of this fraction. So we have to multiply by 1 in the form of multiplying the numerator and the denominator. So when you multiply the same thing in both top and bottom, that really means you're multiplying by 1. So we're not really changing the value, but we're going to change the format. Multiply the numerator and denominator by the complex conjugate of the denominator. Not the numerator, denominator. Because the denominator is the problem. Okay? That's our strategy. So what does that look like? Well, let me rewrite this so you can kind of see it a little bit better. Actually, I do have room here. So what we're going to do is take the denominator, and we're going to say, hey, what's the complex conjugate? Same thing with the plus. And we need to do that same thing to the top because we're multiplying by 1. We're not allowed to change the value, but we can change the format. So what this creates is binomials up here, binomials down here. And so we have now 5 times 4 is 20. 5 times 5, 5i is 25i. 4i times 4 is 16i. And 4i times 5i is 20i squared. That's all the numerator. So that's kind of a lot of work to do there. That is basically the cost of the great thing that's going to happen in the bottom. So we'll see what happens here. So the bottom is going to be 4 times 4 is 16. 4 times 5i is 20i. And negative 5i times 4 is positive. It's positive here. And negative here. And then negative 25i squared. So you may be asking, well, that doesn't look like we helped the situation out. It looks like a lot of work. Well, you got to be patient. This is kind of just showing you what's going on here. So remember that the two middle terms cancel each other out. And then this I squared turns into a negative 1. Okay? Right? So what does this bottom really look like? It just really looks like this. 16 plus 25. That's kind of where you need to get to mentally. And that's based on what we talked about over here. Okay, a squared plus b squared. All right. So that's how simple the bottom can be. But the top, we do have to clean it up. So for the top, we know that this I squared is -1 also. So that's a -20. So the 20s cancel out. Well, let me just write it. -41i minus 20. So basically these cancel in this case. And we get 41i over 41, which then our 41s cancel, giving us just I. Okay, so it's pretty wild that all this stuff just ends up being just I. But that's true in this case. It's not always the case, but the most important part I want you to see is how if you use the concept of complex conjugates, you're always going to get this nice, easy calculation right there. Okay? And we accomplished our goal of eliminating the I from the denominator. Okay, let's take a look at another example before you try some on your own. So this one's going to look different as far as the answer is concerned, but we're going to do the same strategy. We're going to multiply the top and bottom by the complex conjugate. This is basically rewrite the denominator with the opposite sign. Okay, and do that again up here. And so remember, you don't have to do all that work up there. So the point of doing this is to say, hey, the O and the I of FOIL in the bottom are going to cancel out. We just need to do A squared plus B squared. Okay, so just remember that this bottom part is A squared plus B squared. In other words, 2 times 2 is 4, and 3 times 3 is 9. That's it. Okay, you can skip all the other stuff. But in the top, we do have to get that work done up there. So this is going to be 12 minus 18i minus 4i plus 6i squared, which we know that this becomes a -6 right there. So we're going to do 12 minus 6, which is 6, and then these two go together, so that is -22i, and 4 plus 9 is 13. So this is basically correct. This is the answer. But in standard form, we want A plus BI. So we want to go ahead and say separate the two numerators with the same denominator. And voila, we are done. Okay, so you can go ahead and pause that, rewind it, whatever you got to do to look at that again if you need to. But let's go ahead and try 17 and 18 on your own, and then check back with me in a few minutes to see how you did. All right, we're back. So for number 17, 7 over 41 plus 22i over 41. And then for number 18, you have 15 over 58 plus 35i over 58. Okay, so you can always let me know if you have any questions about this. Pause it, take a look at it closely, see if you made any mistakes. But we're going to go ahead and move on from here. The next part is a quick review on operations involving radicals so that we can do some radical complex numbers that you take out in radicals and do some calculations, stuff like that. Okay, now this is the second part or second half of 1.4, and we're going to do a quick review of square roots involving radicals and different operations. So this is quick review, okay? All right, so first of all, what's the difference between 19 and 20? Well, the negative here is on the outside, and the negative here is on the inside. So this is just going to be -3. And this one, like we did before, you go ahead and take out that -1. And so we can turn that into an I, and turn this into a 3, and just rewrite this, and now we have 3i, okay? Okay, number 21, we got to use something that's called the product rule. Oh my goodness. For radicals, okay? And this only applies to real numbers, not imaginary. Okay, so what is this product rule? Basically, it is the square root of two different real numbers. You can basically multiply, those are two radical numbers, you can multiply them together. Okay, that's what it lets you do. We can also go in reverse. Okay, so basically for number 21, you can do 12 times 3, because they're both in the radical. And that's 36, and square root of 36 is just 6. Excuse me. Okay, so for number 22 and 23, we have some more review concepts. For number 20, we can do that product rule in reverse. We have 20, we can separate it out into two different factors with two different radicals. And you don't want to just choose any random pairs of factors that multiply to 20. You want to choose the one that has a perfect square. Okay, so right there we have 4, which is a perfect square. And if you put the 4 in here, that's going to give us a power, an answer of 2. Square root of 4 is 2, and then this just brings, you just bring that down, okay? And so our answer is 2 times radical 5, or 2 radical 5. For 23, we have the quotient rule, which works very similar. If you have two different radicals, but you have the quotient here, you can go ahead and divide those two numbers. So in this case, we have 12 divided by 3 is 4. Well, that's easy, and keep it under the radical. So radical 4 is now just 2. Okay? So the whole purpose of behind those two rules is to keep your product or your quotient in radical form. And then hopefully you have a perfect square that you can turn into a regular number. So when we get to number 24, you may look at 24 and say, hey, what's wrong with that? I don't see anything that we need to do. And you're kind of right, but there's another rule that says you can't leave your answer with radicals in the denominator. So we do need to do something about that. So the radical in the denominator is basically an irrational number. Okay, so that square root of 2 is an irrational number. And so the strategy is to rationalize, to make it go from irrational to rational. How do we do that? Well, just do something to get rid of that radical sign. Okay? So we call that to rationalize the denominator. Okay? What does that look like? Multiply by 1 in the form of the denominator in the bottom and in the top. And that basically is going to give you 1 times radical 2 is radical 2. And then 2 times 2 is 4. And then this turns into a 2. Okay? (25) and 26, we're adding radicals. So the strategy here is to combine like radicals. Okay? And as you can see for number 25, this is a radical 2, this is a radical 3, so these are unlike, which means that this is already simplified. We won't be able to combine any terms here. Okay? So, an example, the example would be something like x plus 2y, okay? You can't put x plus 2y together because those are two different, those are unlike terms, okay? You can't make 3 out of that. But for number 26, again, we see unlike radicals, but the radical 8 can be simplified. And hopefully, from this simplification, we get the same radicals. Hopefully a radical 2. All right? So let's go ahead and break this up using the product rule. We want a perfect square. That's 4 times 2. And then so this square root of 4 becomes a 2. And now we have radical 2, radical 2. Those are now like radicals. Okay, that's very similar to having something like x plus 2x. Okay, so we can do x plus 2x, which is 3x. So here we're going to do the same thing. We're going to do 1 plus 2 equals 3, radical 2. Okay. Okay, so we're done with that quick review of radicals. Now let's combine those concepts with the idea of complex numbers and getting those imaginary numbers out of those radicals. So let's go to our last page of the workbook. Okay. So just remember that you can't take the square root of a negative number. All right. So we need to go ahead and express so first express all square roots in terms of I. Okay. Then secondly, you want to perform the operation, whatever it happens to be. Plus, minus, multiplication, whatever. Okay? So if you mix this order up, you're going to get these wrong. All right. So for example, if you do let's see here. All right, so I'll show you in a minute. So let's see here. We have -9. Remember, you're going to turn this in. You're going to take that -1 out. And this -1 out here. This is kind of the long way to do this. And then this becomes I. This becomes 3. This becomes I. This becomes 7. But I want you to get to the point where you can just write down 3I minus 7I. Okay, so basically, I want you to get to the point where you just go from there to there. Okay, so our final answer then is going to be -4I. So notice that we took out the i's and then we did the calculation. All right, same thing here. Actually, why don't you go ahead and try this one. So the tip here is not only to take the I out, but also to simplify the 18 and the 32. See you in a few minutes. Okay, so you should have gotten -I times radical 2. How did I get that? We'll take out the i's from both terms, simplify each. So notice that I picked the square root for 18, which is, the perfect square for 18 will be 9 times 2, and the perfect square for 32, although 32 has many options to choose from, 16 is the best square root perfect square to use. And then you want to go ahead and simplify. Okay. Now, if you're having trouble with those square roots, remember that your perfect squares that's your first one. The next perfect square is a 4, which we've used before. Next perfect square is a 9. Other perfect square is 16, okay? Next perfect square is 25, so on and so forth. So those are the numbers you want to choose when you're looking at factors. So for 32, even though 4 was a good option, actually the better option was 16, okay? Now, so the last step here, notice that this I radical 2, I radical 2, okay? So these are like terms because they both have radical 2's and i's, okay? So go ahead and try number 29. Let's see if you do better on this one. Okay, so again, I want you to get to the point where you can just write down 3i for the square root of 9 and 4i for the square root of the -16. Just go straight to that. If you don't want to, you want to break it down in a couple more steps, that's fine too. Okay. Now, the last two we're going to do, okay, it's right here. So again, the definition of, well, actually, it's better if we take out this I right now before we start. That way, we have this here already set up. So as you do your FOIL, first your 4 arrows, so if you didn't take the eyes out, you're gonna get these wrong as you move through this problem. All right. So this is a perfect square. This turns into a -1. And we're going to put these together. So what does that look like? Well, we got 25. And then those make -10I radical 11. And then that's a -1. Or -1 times 11. It's basically that. And then we have final answer. It's that there, okay? Okay, so I'm gonna do this one wrong, so you can see what happens if you forget to take out the eyes. Okay, so here I'm gonna do this and do that. I'm gonna get positive 36. Okay, so although this looks right, we did something wrong, and that is right here, okay, which is right there. So, not good. Let's redo this. Okay, whoops. So first, before you do anything, you want to take out all the i's. So this is going to be I radical 12 and I radical 3. And that stays 12. So now when I do this, I'm going to get I squared radical 36. And then I 144, which is 12I here. That looks the same. So the different part here is not only is that a 6, but this right here becomes a -1. Okay? So this one produced a positive 6, and this one produces a -6. Alright, so make sure you take out your eyes before you do the calculation. Alright, that's it for this video. See you in the next one.